All right, let's dive into a thermal paradox that just completely flips intuition on its head. It's a puzzle that's been around for centuries, but for us engineers, it's starting to look less like a puzzle and more like a powerful new tool. We're talking about the Mpemba Effect, and it's all about finding a hidden shortcut to making things cool down faster.
So think about it. Can something hot really cool down faster than something that's already partway there? Your gut reaction and pretty much everything you learned in basic thermodynamics says no way, right? And yet, under the right conditions, it absolutely happens. The real question is, how? Let's break it down.
So here's how we're going to tackle this. We'll start with the engineering challenge itself, look at its surprisingly long history, and then unpack the modern science behind it. After that, we'll see how it even applies at the quantum scale, and then wrap up with the really exciting part, what this means for future technology.
Okay, first things first. Let's talk about why this is such a big deal, especially if you're working in any kind of thermal management.
You know the drill. Whether you're designing a heatsink for the next-gen CPU or developing a new composite material, that time it takes for a system to settle down and reach thermal equilibrium, well, it's often your biggest constraint. It's this relaxation bottleneck that costs you time and just kills efficiency. For decades, we've been trying to manage it, but what if we could just bypass it entirely?
To figure that out, we actually have to look at a clue that's been hiding in plain sight for over 2,000 years.
No joke, the first recorded observation goes all the way back to Aristotle, but it kind of got lost to time until 1969, when a student in Tanzania named Aristotle Mpemba noticed it happening with his ice cream mix. And get this, it's only in the last few years that we've had the supercomputing power to finally understand what's actually happening at the molecular level.
This quote from Mpemba himself just says it all, doesn't it? His simple, real-world observation flew in the face of what everyone thought they knew. And that kind of defiance, that's a classic sign that you're dealing with something far from equilibrium, where the normal, everyday rules just don't quite cut it.
So, what is really going on down there at the microscopic level? This is where recent breakthroughs in computational chemistry give us this incredibly clear picture.
This table really gets to the heart of it. The classical view is simple, right? Cooling is just a straight, predictable line from hot to cold. But the reality is way more interesting. It turns out the initial state, the microstate, matters immensely. The higher energy of the hot water actually gives it access to completely different pathways to cool down, what the research calls shortcuts to get to the final frozen state.
So the key to understanding this shortcut is this idea of a kinetic trap. See, as water cools, the molecules don't just snap into a perfect ice crystal formation. They can get stuck in these messy intermediate arrangements. These traps are just stable enough to slow the whole process down to a crawl. That's our relaxation bottleneck right there.
I love this analogy because it makes it so clear. Think of the cold water as a hiker trying to cross a rugged valley. It keeps getting stuck in all these deep pits and gullies. Those are the kinetic traps. The hot water, though, it has so much energy to start with, it's like a hang glider. It just soars right over all those traps, taking a much more direct, smoother path to the final destination. That extra energy isn't a problem. It's actually its ticket to bypassing all the obstacles.
And the simulations found something else that's completely wild. It turns out hot water actually holds on to a higher number of hexamer seeds. These are the perfect little six-sided molecular rings that are the direct building blocks for ice. So by the time the hot water cools to the freezing point, it's already preloaded and primed to crystallize, while the colder water is still fumbling around trying to get its molecules in order.
Now let's zoom in even further, because this isn't just some weird quirk of water molecules. It turns out to be a really fundamental principle of how systems relax, even in the quantum world.
Yep, the quantum Mpemba effect, or QME, shows that the very same logic holds true for quantum systems. If you prepare a system in an initial state that's even further away from where it wants to end up, you can actually make it get there faster. It's totally counterintuitive, but it works.
Now, to see how, we have to talk about something called the Liouvillean. And don't let the name scare you. For our purposes as engineers, you can just think of it like the master equation that describes all the possible ways a quantum system can relax. And these different pathways, or eigenmodes, all happen at different speeds.
And here is the insight that should get every engineer excited. Just like any complex process, there's almost always one step that's way slower than everything else, the bottleneck.
The quantum Mpemba effect gives us a way to strategically prepare the system's starting point, to give it a very specific initial kick so that this slowest relaxation pathway never even gets a chance to activate. We are essentially designing the starting conditions to force the system to completely ignore its own bottleneck.
And the result here isn't just a small improvement. By knocking out that slowest mode entirely, we force the system to use its much faster pathways. This can literally lead to an exponential speedup in reaching equilibrium. For any process where time is money, that is an absolute game changer. So, let's bring this all back down to Earth. This isn't just fascinating physics anymore. It's a brand new principle we can add to our engineering toolkit.
The potential applications are just incredible. I mean, think about it. Next-gen electronics that can cool themselves faster by briefly heating a specific component. Or cryopreservation that freezes biological samples so fast that damaging ice crystals have no time to form. In the quantum world, this could mean resetting quantum computer memory almost instantly. Or even quantum batteries that can be discharged on demand with unbelievable speed.
You know, the Mpemba effect teaches us this really profound lesson. The fastest path from A to B isn't always the straight line we think it is. By actually understanding and controlling the microscopic journey a system takes, we can start to engineer solutions that shatter what we once thought were fundamental limits. So the real question isn't just how to cool things faster, it's what other thermodynamic speed limits are just waiting for us to break.